Good day, grade 12 learners. Welcome to today's technical science lesson. My name is Musa Zulu. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Right, today, grade 12, our knowledge area is going to be electricity and magnetism, which carries around 33 marks in our paper 1 question paper. And the topic of the day is going to be electromagnetism. Specifically, we're going to be looking at generators, motors, and transformers. This is usually question 10 in our question paper, and it usually carries around 12 plus or minus 12 marks of the question paper. Right, we're going to start again with the structure of paper 1 question paper. And the paper 1 question paper is structured this way. It is structured in two sections, which is section A and section B. Our section A is 10 multiple choice question, which carries around 20 marks. And sometimes section A also has 8 matching items or one-word items, which is about 8 marks. But this is rare for the final examination. Then you have section B, which is for structured or long questions. And that is about usually 130 marks if we do not have the matching items or the one-word items in section A. But if they are the matching items and one-word items in section A, then the section B will be 122 marks. The total of the whole question paper is 150 marks, and the duration is, of course, 3 hours. Right. The topics that are covered in paper 1 are as follows. We have the topics mechanics, which is about 93 marks, weighing 62% of the paper. We have electricity and magnetism, which is going to be our topic for the day, electricity and magnetism. It's about 33 marks of the whole question paper with a weight of 22%. Then we have wave, sounds, and light, which is about 24 marks with a weighting of 16%. Right. Grade 12 learners, remember that you can be in contact with us through our WhatsApp line on the following number: 079 578 2908. 079 578 2908. Please be in communication with us, give us feedback, ask questions if there is a need. All right, let's get onto it. Okay, for today's lesson, in a formula sheet, we're going to be focusing on the electromagnetism part of our formula sheet. And in electromagnetism, the formulas that we need to be aware of are the 3 formulas. But for today's lesson, we're only going to be focusing on this part because when we look at generators and motors, there are no calculations that we need to do there. Right, so the only point where we are going to be doing calculations is when we do the transformers. And this is the only formula for today's lesson that we are going to be considering. Okay, let's get into it then. Generators, right? What is it that we need to know when it comes to generators? Well, the first thing that we need to know is define a generator. And how do we define a generator? We define a generator as a device that converts mechanical energy into electrical energy. And again, the definitions must always be coming from an exam guideline. A device that converts mechanical energy into electrical energy. Right. Now, this sometimes causes problems when learners are now mixing. They start with electrical and end with mechanical, which will be wrong for a generator. So how I help learners to remember this, I always say them, you must always remember a generator. Almost all of us we know a generator and we know what a generator does. Our normal day generator. What generator does, it gives us electricity. Therefore, you must always know the end results of a generator. At the end of the day, it must give me electricity. Therefore, the energy that it tends to must be that of electrical energy. So it converts mechanical energy into electrical energy, because at the end of the day, after using a generator, I get electricity. Right. We must be able to state the energy conversion in generators. And the energy conversion in generators is that it converts mechanical energy into electrical energy. These two questions can be asked differently. This is not necessarily the same thing, because the first one is only a definition. You are being asked to define. So when you're being asked to define, the whole statement must be there. a device that converts mechanical energy into electrical energy. However, if they say state energy conversion, you don't need to include all of this part. You only need to say mechanical energy converted into electrical energy. So they are not necessarily the same thing. One is a definition and the other one only simply states the energy conversion in a generator. Right. We also need to know that generators work on a principle of electromagnetic induction, which is extremely important, and we are going to look at it as we start with the working of simple generator. We also need to know, grade 12, that there are two types of generators, and type number 1 is an AC generator, sometimes referred to as an alternator. And an AC generator is a device that converts mechanical energy into alternating current energy. The abbreviation AC there standing for alternating current. So what an AC generator does, it converts mechanical energy into alternating current energy. And the second type of generator is a DC generator. A DC generator is a device that converts mechanical energy into direct current energy. The abbreviation DC there, okay, again representing them direct current energy. So those are the two types of generators that we need to be aware of: the AC generator and the DC generator. Right, let's take a look into the AC generator. So as we've said, generators work on the principle of electromagnetic induction. So that also tells us we must be able to define electromagnetic induction. And what is the definition of electromagnetic induction? It is the process of generating electricity through motion. So that's when we are generating electricity through motion. And how does this happen? This happens when you have a conductor and you have magnetic field, and you have a conductor that is moving relative to magnetic field, and the conductor is actually cutting the magnetic field perpendicular or at some angle greater than 0. So when the conductor cuts the magnetic field, electricity is generated. So there must be movement, a relative movement between the magnetic fields, where you're going to have a magnet. The magnet is obviously going to have magnetic field around it. Then you are going to have a conductor, and they are moving relative to one another. And electromagnetic induction tells us that there is going to be electricity that is going to be generated. So that's what actually happens in a generator. A simple generator will look something like this, where you are going to have a magnet, right, and another magnet here. And these two magnets are showing the polarities of north and south. And inside this generator, we are going to have this conductor that we are going to call a coil. You are going to have a coil. And once we have the two magnets, between the two magnets, there's going to exist a magnetic field. There's going to exist magnetic fields, and the magnetic fields are always going to pointing from the north to the south. So what we are saying, or what electromagnetic induction is saying, that if I can take this coil and I can move this coil across the magnetic field such that it is cutting the magnetic field, maybe I move it up and down, what is going to happen there is that in this coil, which is a conductor, I'm going to generate electricity, meaning that there is going to be what? There is going to be current that is going to be induced here. We're going to induce current. We're also going to induce EMF. Right. So the first important thing that we must be able to do when it comes to a simple generator like this, we must be able to determine the direction of the current that is induced. And how do we do that? The way we do that, we look at the right-hand rule, right? This is, some people call it Fleming's right-hand rule. Some people call it the right-hand generator rule. I call it the right-hand FBI rule, to ensure that I always remember it. I call it the right-hand FBI rule. And how does the right-hand rule actually work? The right-hand rule gives us the direction of current that is induced in the coil in my generator. So the right-hand rule works like this. You hold your fingers such that your thumb, your forefinger, and your middle finger are perpendicular to each other like this, right? And then you must know what all these three fingers are representing, which is the reason why I'm calling it the right-hand FBI rule. You look at the thumb. The thumb is always going to represent the direction of motion. Why are we saying direction of motion? Remember, for us to induce EMF or current here, we must move the coil. So the coil is going to be rotating inside these two bar magnets. So we must know the direction of motion. Is it either going clockwise or is it going anti-clockwise? So once we know the direction of motion, it's going to be easy for us to determine the direction of the induced current. Number two, the four fingers represents the direction of the magnetic field. The direction of the magnetic field, which we know they are always going to moving from the north to the south. While the middle finger will then give us what? Will then always give us the direction of the current. So we have our thumb, we have our forefinger, and we have our middle finger. This is the direction of the motion, which can also be said to be the force. Therefore, if it is the force, we can represent it with the symbol capital letter F. And the forefinger represents the direction of the magnetic field. And what is the symbol that represents the direction of the magnetic field? It's B. And the middle finger then represents the direction of what? Of current. And what symbol do we use for current? We use I. That's why we are calling it FBI. A simpler way of trying to remember this right-hand rule, right-hand FBI rule. So how do we use this right-hand FBI rule to determine the current? Let's say they tell us that this coil is being rotated clockwise like this. We know the direction of the coil, because they have to always tell us the direction of the movement of the coil. We have to always know the direction of the movement of the coil in a generator. So in a generator, we'll always know the direction of rotation. In a generator, we'll always know the direction of the magnetic field. The only thing that we must determine as learners is the direction of the current. As it is said here, in generators, we are always looking for the direction of the current. Nothing else. We are always looking for the direction of the current. We'll always know the direction of the motion. We'll always know the direction of the magnetic field. Then we can determine the direction of the current. So let's try and determine the direction of the current in this generator that we have here. Right. So if we are moving clockwise in this direction, that tells us that this pink part must be going up. This pink part must be going up. So we know the direction of the magnetic field going from north to south. We know the direction of the rotation of our coil going clockwise. Then let's determine the direction of the current. So we start by making sure the forefinger follows the direction of the magnetic field, which is going to be in this direction. And let's check, is the thumb following the direction of the motion? Is the thumb following the direction of the force? Yes, it is. When you look at the pink should be moving up. Therefore, it tells us that the current is going into the page there. The current is going into the page. Maybe we can even label this as A, B, C, and D. So the current goes from A to B. So our direction of current will be like this. So if this is true, then it tells us that the direction of the current here will continue like this, and the direction of the current will be going in the blue part, should be going from C to D. Right. But we can also try and confirm that. Is it true that the direction of the current will be going from C to D on the blue side? Let's also again try to use our what? Our right-hand FBI rule. Let's make sure the forefinger follows the direction of the magnetic field, as the direction of the magnetic field moving from the north to the south. Now let's make sure that the thumb follows the direction of the motion. What is the motion on the blue side? Is it going up or down? It should be going down. If it goes up on this side, it should be going down on the other side. Therefore, I should flip and make sure that the thumb is facing down. So that gives me the direction of the current going out of the page, going from C to D. That confirms that the direction of the current must be moving from C to D in this direction. And that's simply how we determine the direction of the current in a generator. It is as simple as that. You use your right-hand FBI rule, where the B represents the F represents the force or the direction of motion. The forefinger represents the direction of the magnetic field, and the middle finger represents the direction of the current. You will always be given the direction of the force, the direction of the magnetic field. You only need to determine the direction of the current. It should be simple. It should be just an issue of what? Taking your mark, as easy as that. Right. However, if a generator just looks like this generator is not complete. Right. So, because a generator converts mechanical energy into electrical energy, a generator must also have a load, something that it is going to be giving its electricity to. In this case, let's use a light bulb for the load. So a generator, for it to be complete, maybe we will connect it like this. Then the current will be able to flow through and give us electricity there in a light bulb. But let's think about this generator that I have right here. If this generator starts rotating, the coil starts rotating there in this generator, right? What we're going to have here, we're going to have a problem here, because now these wires, as you see, if they are connected like this and it's rotating, these wires are going to start twisting and tangling with each other. So there's going to be a problem of wires twisting and tangling with each other there. So if you put your generator like this, that will not be a very good designed generator. Therefore, that's why they decided to say, let's not connect these wires directly into the coil. Instead, let's have something that is just simply going to touch the coil and making sure that it's maintaining electrical contact between the load and the coil. So what they used for that, to avoid these things having to twist and turn and tangle with each other, they used the carbon brushes. They said they are going to put brushes here. They are going to put brushes here, which are called carbon brushes, right? These brushes are called what? Carbon brushes here. They put the carbon brushes here. Then these carbon brushes, all they have to do is do what? Is just maintain contact or electrical contact between the load outside and the coil in the internal circuit. Right. But now, if then we leave it like that, another problem is going to arise here, right? And I need you to imagine, and I need you to be very, very careful here and pay attention as to the reason why we have to put the next design in our generator. Now, if we move, the coil starts rotating, you would notice that the pink will go up, right? And it will go here, and the pink will then go down and cut the magnetic field here. Now, when the pink cuts the magnetic with the current as the coil is rotating is changing direction, or is what? Is alternating. So in the internal circuit, we are having alternating current that is busy changing direction. So if we just leave it like this, when B gets to that other side, the current will then will be changing direction. And that will not work in the external circuit here, because in the external circuit will be just the current maintaining the same direction. So how do we make sure that the current also is transferred as AC in the external circuit? What they used there, they put in rings. They used rings. These rings, what are they supposed to do? They are putting the rings that are supposed to ensure that the same contact is maintained with the same part of what? Of the conductor on the load. So these rings are supposed to just maintain only the same part. As this thing is moving, it will only be connected to this. It is not going to go from one side and connected to the other side. It will only be connected to this side, while this will always be connected to this side as the rings are moving. What are the rings actually doing as they are moving? They are slipping. They are slipping through the carbon brushes. They are slipping through the carbon brushes. So if these rings are slipping through the carbon brushes, what are we going to call them? These rings must be called what? Slip rings. Why are they called slip rings? They are called slip rings because they are just slipping through the carbon brushes, maintaining that contact between. So what is it that we need to know? We need to know the design of a generator is going to have a coil, magnet. It's going to have carbon brushes that are there to maintain electrical contact. It is also going to have these rings that are slipping through the carbon brushes, and these rings, their job is to ensure that the alternating current that is in the internal circuit is also the alternating current in the external circuit. So once the generator has been designed properly, it should look something like this as we were talking. If you can see here, here's our coil, and here are these carbon brushes. These are the brushes, the carbon brushes here. And we also have these rings. If you look at the blue ring, it is only connected to the side, and it will always maintain a contact with these carbon brushes. It will never come into contact with the other carbon brush. And if you look, the pink one is only connected to this carbon brush, it will never come into contact with this carbon brush as it is busy rotating. So they will always slip through one carbon brush each, and they are slipping. Hence, they are called slip rings. They are just slipping through the rings. This is slipping through the rings as in a slippery surface. So they are slipping through the rings. So that's what we need to know. A generator is going to have carbon brushes. A generator is going to have slip rings. A generator is going to have a coil. And a generator, of course, is going to have a load where electricity is going to be provided. Hence, it is converting mechanical energy into electrical energy. So at the end of the day, these are the things that we must know, and this is what a generator, a simple generator, looks like. As we were saying, they are carbon brushes here, and these carbon brushes, their job is to what? They are there to maintain electrical contact between the load and the coil. And you also have slip rings, which are just slipping through the carbon brushes. I'm repeating that because it's easier to remember when you understand why are these brushes there. They're just slipping through the brushes, hence they are called slip rings. They are slip rings, and they are there to do what? To transfer AC in the internal circuit, because in the internal circuit, the current will keep on changing direction as the coil is rotating. But we want the AC to be AC also in the external circuit. So the current must also change direction in the external circuit. So we use slip rings for that. They transfer AC or alternating current in the internal circuit to AC in the external circuit. Right. We can also be asked to draw a graph of EMF or potential difference versus time graph for the AC generator. And how do we represent that graph? Well, what we need to understand is that according to electromagnetic induction, EMF or the electricity will only be induced when the coil cuts through the magnetic field. If the coil does not cut through the magnetic field, then EMF is not going to be induced. It must be cutting at least at 90 degrees or some angle above zero. If the coil is parallel to the magnetic field, then there won't be any EMF that is going to be induced there. So if we are looking at our diagram here, here's our magnetic field going from north to south. As you see there, the angle between the magnetic field and the coil itself is zero. So that means they are parallel to each other. As you see, the magnetic field is around here. It's not cutting. It is not cutting the magnetic field. The coil, is around here. It is not cutting the magnetic field. And then it starts rotating. As it rotates from here to here, 90 degrees. And when it gets here, it is cutting, which means it now produces the maximum EMF, also inducing the maximum current there. And as it rotates to the other side, it is now at 180 degrees from 0 here to 180. It is not cutting anything. And as it comes back, it cuts the magnetic fields again at 270, producing maximum. So this is how, when it is at 0, it produces 0 EMF. And when it rotates and through an angle of 90 degrees, it's going to produce the maximum potential difference, or even the maximum current there, or even the maximum current. And then when it keeps on rotating through an angle of 180, it will go back to producing no EMF at all, or inducing no EMF, because it will not be cutting the magnetic field. And then because this is an alternating current, the current is changing direction. And when you go to a 270 degrees going to the other side, the current would have changed direction there. Now it will be producing the maximum negative EMF, the maximum negative EMF. to the other side. And as it rotates through 360 degrees doing a revolutionary, it will go back to what? To 0. Meaning that as it continues rotating, it should produce again another maximum here, going back to 0, going back to the maximum negative, going back to 0 for as many revolutions as the generator is going to be doing what? Is going to be rotating. So this graph could be a potential difference versus time graph, or it could be a current versus time graph. The shapes of the graphs look the same. So if they are saying current versus time graph, you are going to draw it the same, with the exception that on your y-axis you are going to represent as current in amperes, and here you are going to represent as time in seconds. That way you have represented the graph of an AC generator. Right, then let's take a look at a DC generator. Like an AC generator, a DC generator also works on the principle of electromagnetic induction, the process of generating electricity through motion. Then that means we must have a coil that is moving relative to magnetic fields, cutting them at 90 degrees for maximum EMF, or at least at some angle greater than 90 degrees. If it is at 0 degrees, there will be no EMF that is induced there. A DC generator converts mechanical energy into direct current energy. Unlike an AC, if you remember in an AC there, we said we want the alternate current coming from the internal circuit to be the alternate current in the external circuit, which is the reason why we introduce slip rings. So that's why the slip rings are there, so that they transfer in alternate current from the internal to alternate current in the external circuit. But in a direct current or DC generator, we want there to be a direct current, unidirectional flow of current in the external circuit. So the way that the DC generator works is very, very closely similar to the AC generator. Its design is almost exactly the same, almost, not exactly, but it is almost the same. Then you are going to have there 2 bar magnets of north and south poles. Then obviously with those 2 magnets comes the magnetic fields going from the north to the south. You are also going to have the coil, and they are also going to give you the direction of rotation. Let's say this time around our coil is rotating anti-clockwise. So since this is also a generator, we are going to be expected, to determine the direction of current. In generators, we always look for the direction of current. And how do we do that? We use again our right hand FBI rule. That's what I call it. It's actually the Fleming's right hand rule. It's some other people call it the right hand generator rule. I remember it by saying it's the right hand FBI rule. Why FBI? Because I know I need to know my FBIs. What are the FBIs? That's the direction of motion or the force, which could be represented by a symbol capital letter F. I could even write it here on my hands here, capital letter F. And the forefinger represents the direction of the magnetic field, and the symbol of the direction of the magnetic field is capital letter B. And the middle finger represents the direction of the current, while the symbol there is capital letter I, making FBI. A word or an acronym that I believe is very, very easy to remember. So you have your FBIs there, and you must make sure that they are all perpendicular to each other. We are still using the right hand. When it comes to generators, we always use the right hand. We must determine the direction of the current yet again. So let's check the direction of the current if now the coil is moving in an anti-clockwise direction. We will start with the blue side. Let's start with the blue side. We start by holding our right hand rule like this, and we make sure that the forefinger, we always start with the forefinger. It's very, very easy when you always start with the forefinger. So make sure that the forefinger follows the direction of the magnetic field. Let's start there, north to south, right? Then let's check, is the thumb following the direction of the force? What is happening on the blue side? Are we moving up or down? as you can see there, if we are going in this direction, the blue side should be moving up. The blue side should be moving up, and the pink side should be moving down. The pink side should be moving down. So let's hold it. Direction of the magnetic field. The thumb points up because the blue side is moving up. Then the direction must be going into the page. And if we were to label this as A, B, C, and D again, this time around the direction of current is going from D to C. The current moves from D to C according to our right-hand FBI rule. I follow the direction of the magnetic field. Here's the direction of the magnetic field. I follow the direction of the motion there on the blue side. It goes up. Then it gives me the direction of the current. Right. Then if I am right in what I'm doing, then the current here, because the current cannot just turn on the way, the current should continue like this. Then the current here should be going from B to A, if I am right in what I have done. But I can confirm whether I am right or not. I can't just take that as my conclusion, because I still have my right-hand FBI rule. So let's go and confirm on the side AB, or the pink side. Is the direction of the current from B to C? Again, we use our right-hand rule. We make sure that the north, or the direction of the magnetic field, points from north to south. Here's the direction of the magnetic field pointing from north to south. Right. Then let's check the thumb, which is the direction of the force, the F, or the direction of the motion. In the pink side, where is it going? Is it going up or down? If you look at it, it goes down. If you think about it, if this side it goes up, the other side should be going down. Therefore, I should turn my hand like this. And this is all you do, grade 12. There is no need for you to twist your hand to an extent where you almost break your hand. Your hands must always be either facing this direction or facing this direction. That way you will always get the direction of the current. So we should turn our hand like this. That way we are getting the direction to be coming from out of the page. It is coming from B to A, which means even the current that we determined here should also be correct. And that's how, again, we determine the direction of the current in a generator. And I'll repeat and say, in generators, we are always looking for the direction of the current. And we are always using the right-hand FBI rule. Fleming's right-hand rule, the right-hand generator rule, whatever you call it, from all of those things. As long as you are able to use and apply it, it is fine with me. Right. So again, with a DC generator, like we did with an AC generator, this generator is incomplete. What does the generator need? It needs a load. Remember, we are converting mechanical energy, which is the rotation part of it, into electrical energy. So they must be where we are taking the electricity to. So let's have a load, which is, again, we'll make it a light bulb. It could be anything. And we connect it directly like this, right? What could be the problem again here? We have a problem of the design. We have designed a very, very poor generator, if we put it like this. How come? If this generator starts rotating, we start rotating this generator, we're going to have problems with these wires as they twist and turn, and they are tangling with each other. Therefore, we cannot put the load directly into the coil. What should we use? Let's introduce the carbon brushes. Let's introduce the carbon brushes to avoid this thing of wires tangling and turning. It's a design. We are introducing the carbon brushes. As long as these carbon brushes can maintain contact with the coil, we will know that we'll always have electrical contact and electricity will be able to flow. So let's have carbon brushes that are going to be there to do what? To maintain electrical contact between the load and the coil. That's why the carbon brushes are there. Okay, so again, let's discuss the issue of the current changing direction. Okay, now this time around, if this one goes to the other side, we're going to consider the blue side this time around. If you look at it, if it goes up and then it turns to the other side, that's the blue side that I'm talking about. When the blue side gets to this side, the blue will now be going down. If we are doing a whole revolution, the blue will now be going down. If the blue is going down this side, then the current cannot be from D to C. I hope everyone can see that with me. If I take this and it's on the other side and now it goes down, the current cannot be moving from D to C. Why? According to the right-hand FBI rule, I will be checking the current like this, right? I will be checking the current like this because blue will now be going down, which means the current will now be moving from C to D. It will be moving from C to D. Telling me what? Telling me that as I rotate my coil in this generator, the current will keep on changing. So as blue gets this side, the current goes from C to D. As I come to the other side, the current goes from D to C. So do you see that it keeps on changing direction as it moves? However, now, if that happens, and if this maintain contact with only this side, and this one maintains contact with only this side, then I will have a problem because this will transfer AC to AC outside. But I don't want that to happen. Remember, I am dealing with a what? A DC generator. I want direct current, right? So what do I do to have the direct current? What I introduce are rings again, a different type of a ring. I introduce a different type of a ring called a what? A split ring, right? Why is it called a split ring? It's called a split ring because it has a split in between, right? So these ones are carbon brushes, and this one is called a what? A split ring. This one is called a split ring, different from the slip rings, which were just slipping through the carbon brushes. This one is called a split ring because it has a split. However, it does have another word for it. It is also called a what? A commutator, right? But the easiest one to remember for me is split rings because if I look at it, I see a split in between. Therefore, I call it a split ring. So what is the split ring going to help us with? The split ring helps us that I need this current to be in one direction. In the external circuit, I need the current to continue moving like this. So to ensure that the current continues moving like this, when the blue goes to the other side and it turns to the other side, I need this side to then connect with this side because remember, it's going to change direction. The direction will be coming out of the page. So I need the blue, when the blue turns, as the blue goes to the other side and it goes down, I need it to be connected to this side. Therefore, it's going to give me a current in one direction. And when pink comes back, it must be pink connected to this side. That way, it will always give me a current in one direction in the external circuit. So that's why we are going to be having split rings there. Split rings are there to do what? To convert alternating current in the internal circuit to what? To direct current in the external circuit. Alternating current in the internal circuit, I mean, to direct current in the external circuit. The current in only one direction, right? What is it that is extremely important for you to know? You must know that a generator is going to have a coil. You must be able to determine the direction of the current in that. You must know that a DC generator is going to have split rings, right? A DC generator is going to have split rings. You must also know that there are going to be carbon brushes as well there. And because it is a generator, it is going to have a what? It is going to have a load. A DC generator will look something like this, right? When you look at the generator and a properly drawn generator, unlike the one that I was drawing there. As you can see there, here are our two magnets, and here is the coil, right? Even though this one is moving in a different direction, you can see there. Here's the split I am talking about. There is a split in this ring. There's a gap in between. Hence, we call it a split ring. But another word for it is also commutator. Use the word that you can always remember. Again, it's a generator. It must have a load. A generator must have a load because we are converting mechanical energy into electrical energy. We give any electricity to this load. Yeah. So it is going to maintain the same direction. This direction will always be the same direction in the external circuit. Here it will change as the coil is rotating. But when this guy rotates, the current in this case should be like this, and here it should be like this according to what has been given there. When this guy goes to the other side, right, with the current that will be now moving in that direction, it will now be in contact with this carbon brush, maintaining the same direction. while this one comes here, it will be now in contact with this brush, maintaining this direction in the external circuit. So we have again here carbon brushes, and they are there to do what? They are there to maintain electrical contact between the load and the coil, as they were doing with the AC generator. However, we have also split rings in DC generators, split rings or a commutator. And what does split rings or commutator do? They convert AC alternating current in the internal circuit into DC direct current in the external circuit. However, what is the most important thing that I want you to know? I want you to be able to look at a generator and be able to tell whether this generator is DC or AC. Now, how do you differentiate between the two? You only use your rings. It is not a complicated thing. The only thing you check to determine whether this generator is DC or AC. Even if you don't understand why the split rings are there, you don't understand why the slip rings are there, you must at least be able to tell whether this one is a DC generator or it's an AC generator. And how do you do that? You just look at the rings and only the rings. Once it's a split ring, that's a DC. And once it's slip rings, that is AC generator. All of them are going to have carbon brushes, and all of them are going to have a coil. All of them are going to have the magnets there. All of them are going to have a load, since they are all generators, converting mechanical energy into electrical energy. Right. Again, with the DC generator, we must be able to draw the PD, potential difference, versus time graph, or current versus time graph. We should be able to draw these two graphs. These two graphs are going to take the same shape and the same form. We look at the same thing as we did with the AC generator. We must look at the direction of the magnetic field. Say we have direction of the magnetic field moving from here, which means this will be our north, and this side will be our south. The magnetic fields are always moving from the north to south. As you can see here, as I was talking about last time, if the magnetic field, let's consider only this part. Let's consider only this part. This part here is on top there, meaning the magnetic fields are just going through this loop here, or this coil. So this conductor, or even this conductor in here at the bottom, is not cutting the magnetic field. It's not cutting the magnetic field. It's right here on top. And if it doesn't cut the magnetic field, we cannot have a EMF that is induced. It must cut the magnetic field. There must be some relative motion between the two magnetic field and the conductor. So therefore, this one is not cutting. The magnetic field are just simply moving through it. Therefore, we will have zero EMF that is induced there. Hence, we're having the zero, the side. The zero that is here, showing that there is no EMF that is induced. And if there is no EMF that is induced, there will be also no current here. Even if this graph was for current, there will be no current measured in amperes there. Right. However, once the coil starts rotating and then it goes to the other side, meaning now it cuts the magnetic field. Once it goes here, it cuts the magnetic field. From here, it has rotated 90 degrees to here. Once it cuts, EMF is going to be induced, and maximum EMF will be induced there. Maximum EMF at an angle of what? Of 90 degrees as time progresses. Right. Then from here, it should go underneath because it's rotating. If you are just only concentrating on this one, here it is. Here we will find it here. Here it is here. And then here we'll find it underneath. That's when it has done an angle of 180. It was 0 here, right? And then here it did 90-degree rotation. And then it started cutting the magnetic field, producing maximum EMF. And then it was going underneath as it rotates here. It has at an angle of what? 180. And there it does not also cut the magnetic field, which means we are inducing zero EMF again and inducing zero current at that point in time. Right. Now then it will rotate again to 270. But remember, now the DC, as it rotates to 270, unlike the AC, the current is not going to be changing direction. So we are not going to be having the minimum or the maximum negative EMF here. The maximum negative EMF. We won't be having the maximum negative EMF this side because the direct current does not change direction, so it maintains the same direction. So after it goes from 0, it will go back to maximum positive. So here, as it goes to 270, this is where we will find it. And we are tracing only this part. We are checking this part of the conductor goes from 0 here, not cutting the magnetic field they are going through, but when it turns and does this, it starts cutting. If you are looking at my fingers as the magnetic field, it starts cutting the magnetic field, right? It will induce maximum EMF, will have maximum current as well there, and then it goes underneath as it rotates. Underneath here, it is rotated 180 from here. If this is our 0, this is our 90, this is our 180. Then we'll be introducing 0 EMF again, or inducing 0 EMF, because it is not cutting the magnetic field there. And then again, as it rotates through 270 degrees, it will again induce maximum EMF yet again there. And remember, it is not changing current because it is direct current generator. And then if it goes back to 360, it will induce a 0 again, meaning that if we were to continue here, we will go back to maximum, going back to minimum, going back to maximum, going back to minimum. That's what the shape that is taken by the graph of a direct current. Always goes to maximum, back to minimum, maximum, back to minimum. That is if it's a potential difference versus time graph, and or it is a current versus time graph. So if we were drawing, if this was a potential, if we were drawing the current, we'll write current here, right, in amperes, okay, and then we'll write time in seconds. Therefore, our graph should be something like this. Minimum, maximum, minimum, maximum, right? As it goes from here to here, that's a whole revolution. And it goes from here to here, that's a whole revolution. So this is half a cycle, this is a full cycle, this is half a cycle, and this is also a what? A full cycle. So this is the shape that is going to be taken by a graph of a direct current generator, a DC generator. And it's going to be the same shape that is going to be taken even if it was potential difference versus time graph. So you should be able to draw this graph, or at least sketch the graph, because most of the time the examiner usually asks that we sketch the graph. So meaning that there are no need for numbers to plot and all of that. We just simply looking for the shape that the graph is going to take. So after we are able to differentiate between the two generators, we should be able to differentiate between the shapes of the graph from the two generators. One is going to have the maximum and also the minimum changing direction, that's the AC, while this one will always have the maximum to 0, back to maximum, back to 0. Always going to be having that. That's the direct current generator graph. We should be able to draw these graphs as they could be asked in our final examination. Right. So here's a comparison between the two graphs here. When we compare between the DC and the AC, the two graphs are going to look like this. As I was saying before, this will be your potential difference versus time graph. As you see here, we have V representing the potential difference here, and this is the positive and the negative maximum, positive maximum, negative maximum. In the DC generator, you will not be having any negative maximum because it is direct current. The current does not change direction. So it only goes from 0 to maximum, back to 0, back to maximum, back to 0, back to maximum, back to 0, and so on and so forth. And I repeat, even if we were doing current, the same shape should be taken by these graphs. When we go to the AC, we're going to have where we have 0 and we induced maximum, and then we induce 0 at 180 rotation, and then we are also going to have negative maximum, We also have negative maximum on AC generators, because AC, they alternate the current. Yes, hence it's called alternating current. It changes the direction of the current. So it goes in the positive direction. It also goes in a negative current direction, going back to zero, going back to maximum, back to zero, minimum, and also back to zero. And by the way, a full cycle of an AC generator will be this one. If I go to maximum to zero, this is a half cycle, right? And then if I go from here to here, this will be a what? A full cycle. So if they say sketch a graph showing a full rotation, only one rotation, then your graph should have 2 half cycles, right? Depending on where the rotation actually started. If the rotation started from zero, it should start from zero. If the rotation started from a maximum, your graph must also start here from a maximum. So if the rotation starts from where the graph, where the pole was cutting, and then it moves like this, then back to where it was cutting, then like this, your full rotation or your graph should start from a maximum here. But if the rotation starts from zero here, then we start rotating, then your graph should start where? It should start from a zero. And this is a half cycle, and this is a full cycle. This one is a half cycle. If we go all the way here, we have 2 full rotations that are done by this coil represented by this graph. While here, a full rotation will be represented like this, from zero to maximum back to zero, and then back to maximum back to zero. This from here, this represents a full rotation. This is a full rotation. So it goes from zero to maximum back to zero, and then it goes to maximum back to zero. This is what you call a half cycle. This is a full cycle. Half cycle, and then here, full cycle. So here we are having, again, if we go back to the point here we are having 2 rotations as well. So it's 2 rotations for this one, and it's also 2 rotations. It is extremely important that we are able to draw these graphs, and as they could be asked. Right. So now I want us to look at advantages of alternating current over DC current, right? Or alternating AC generators over DC generators. So some advantages, it's a lot. I've only named 4 advantages that are there. There are a lot of advantages, and it is important that you know, because if you know, in our real life, AC current is the one that we encounter the most. AC current is what we get the most. And what is the reason for that? The reason for that is that alternating current has more advantages than the disadvantages, and it has more advantages over the DC current. That's why it's the one that is mostly used in our everyday lives, right? So what are these advantages that are being talked of here, AC versus DC? Well, AC generators are more efficient. It is said that AC generators are more efficient. They work very well over the DC generators, right? And AC can be transmitted over long distances. And this one is a very, very important one. AC can be transmitted over long distances. It is easy for it to be stepped up as it goes from where electricity is being generated. They will step it up to hundreds of thousands of volts, right, or kilovolts, right? And then it travels there, coming to us, to our houses. And when it gets to our houses, maybe it's coming as 11,000 volts, for example. I'm making an example there. And then now we must have the potential difference entering our houses, right? It cannot enter our houses as 11,000, because that would be extremely dangerous. So what must be done? A transformer has to be used where it's going to be stepped down, right? So and then it stepped down to the 240, that is 230, 240 that is allowed in our household. So, but the big idea there is that it is easily transmittable over a long distance. So its AC can be transmitted over a long distance. Unlike DC, it is extremely difficult to do that for DC. So that's one advantage there. And then again, AC generators are generally less expensive. They said that AC generators are less expensive than DC generators. And the last one that I have there is that AC generators are simpler to design and build. So those who designed generators, they find that it is simple to design the AC generators and build the AC generators than it is to design the DC generators. So those are some of the advantages of AC over DC, right? There could be more. You could also, in your own space, in your own time, look for more advantages of AC over DC. I'm sure you are going to find more that maybe you might like. As long as they are correct, they could also be used in a case where this question is asked in an exam. You state all those advantages of AC over the DC generator. Right. Okay, now let's talk about DC motors. Okay, so we've talked about generators. We said we have AC generator and a DC generator. We've looked at how they operate, right? Now we have also looked at the differences and the similarities between the two. Now it's time to look at a DC motor, right? A DC motor or a motor in general, the definition there is that it's a device that converts electrical energy into mechanical energy. So a motor changes electricity into mechanism. A motor needs electricity to provide mechanism. Think of simple thing. Think of your motor gate. For your motor gate to work, it needs electricity. It needs a power supply. It needs a battery. So that's how you think of motor. Think of a washing machine. You cannot use a washing machine without having power source or power supply, some sort of electricity or some sort of battery. Those things have motors. Think of a microwave oven. It can't work without electricity. So a motor needs electricity. Unlike a generator, we said a generator gives electricity. A motor needs electricity. So we say it converts electrical energy into mechanical energy. And we must be able to state the energy conversion there in motors. And the energy conversion is that it is electrical energy converted into mechanical energy. And then I repeat again, these two are not the same thing. If they ask you to define, we need the whole definition. If they ask you to state energy conversion, you only tell us the energy, where it comes from to where it is now. It comes from electrical energy to mechanical energy. That's all you need if they say state the energy conversion. So they are not the same thing. Yes, they look similar, but they are not necessarily the same thing. Excuse me there. Right. So as we said, generators work on the principle of electromagnetic induction. Motors also have their own principle, and the principle that motors work on is the principle of motor effect. So motors work on the principle of motor effect. And what does the principle of motor effect says? It says if I have a current carrying conductor and we place it in a magnetic field, it will experience a mechanical force. What that means is that if I were to take a power magnet is going to have magnetic field, obviously. And I take a conductor, right? But this time around, my conductor already has the current. Unlike in a generator, if you remember in a generator, I only took a conductor and I moved it relative to the power magnet and I induced current that way, right? So current was induced by moving a conductor relative to a power magnet. This time around, I take a power magnet and I take a conductor that already has current flowing through it. If I then try to move that or place that conductor in that magnetic field, it should experience a force that pushes it. And this force is going to cause it to do what? To rotate. This force is going to cause it to move. It will experience a mechanical force. That's what a DC motor or the principle of where the DC motor works on. Okay. Now, a motor is constructed almost the same way as a generator. However, instead of producing electricity, it uses electricity to what? To rotate. So if I were to just quickly finish up my motor here, my motor needs electricity because we say it uses electricity. My motor needs a power supply. So I'll put in that cell over there where this is going to be the positive terminal. This is going to be the negative terminal. If this is the positive terminal, that already tells me the direction of current. Already I know the current moves in this direction. The current moves in this direction in this motor of mine. Because the current, conventional current, moves from the positive terminal to the negative terminal. Right. In generators, we were determining the direction of current. I emphasize this point. We are always determining the direction of current in generators. In motors, we always determine the direction of the rotation or the force. where is this going to be pushed, because we said it will experience a mechanical force. In which direction will this force be? That's what we want to determine. And how do we do that? We use the left hand FBI rule, Fleming's left hand rule, the left hand motor rule, for those that call it like that, left hand rule, the Fleming's left hand rule, the left hand motor rule, or the left hand FBI rule, as I like to call it. Again, why am I calling it FBI? We are talking the force represented as F, direction of magnetic field represented as B, direction of the current represented as I. So this time around, we are using the left hand. We make sure that all these fingers are perpendicular to each other, and as we hold them, we are looking for the direction of the motion. So we are always going to be given these two. So we'll always know the direction of the magnetic field. We'll always know the direction of the current. So let's determine the direction of the rotation here. The direction of the rotation, let's first follow the direction of the magnetic field, north to south. Here's the north to south here, right? Where is the direction of the current going here? The direction of the current goes into the page. So I should just flip my hand, telling me that the direction of rotation on the pink side should be going down. Simple as that. We go to B. If this is going down, the blue side should be going up. Let's confirm if that is true. Again, forefinger, follow the direction of the magnetic field from north to south. Direction of current must be going out of the page, as I am pointing here, meaning that the direction of force faces up. So this means this was also correct. So it means the direction of this motor will be anti-clockwise. It will be anti-clockwise. That will be the direction of the motor. It will be rotating like this in an anti-clockwise direction. However, this motor is not complete like this. We'll again have the same issue as it rotates. There was going to be the tangling of the wires here. Therefore, again, we have to use the what? We have to use the carbon brushes. We have to use the carbon brushes, right? And to maintain a direct current, since this is a DC motor, again, we are going to use what? We are going to use our split rings. Take these rings that have a split in between. That's what we are going to use for DC motors. Right. So a DC motor would look something like this. As we were saying there, here's our coil, right? Okay. This time around, the direction of current will be moving like this. If you are seeing that, here's the positive terminal. So current must be moving in here. Current must be coming in towards the negative terminal this side, right? They are telling us it goes up here, it goes down here, meaning it moves in a clockwise direction. Let's confirm if that is the truth by using the left-hand FBI rule. Hold our fingers like this. What is the direction of current? The direction of current goes into the page here. But what is the direction of the magnetic field? They go from north to south. So if I am checking this side, I can tell that it is going down, meaning that this direction they have given here is correct. And let's look at the other side. The direction of a magnetic field going from north to south. But what is the direction of current? Is it going in? No, it's not going in, it's going out. So I must change it, telling me that the direction of motion is going up, telling me that this again is correct. So the direction of motion of this motor is in a clockwise direction. And when it comes to motors, this is all we need to know. We just need to know that motors need electricity. So there must always be a what? A power supply. There must always be a power supply. Immediately you see a power supply. That is not a generator. A generator must have a load. Once you see a power supply, you are dealing with a motor. And the only motor that we're going to be dealing with is a DC motor. So you expect to also see what? Commutator there, or split rings, right? And you're also going to see this thing called what? Carbon brushes. And you see those carbon brushes, obviously with a coil and those two magnets. And you are always going to be determining the direction of motion. You're always going to be determining the direction of motion using the left hand FBI rule, where F is the force B is the direction of magnetic field, and I is the current. So for motors, we use the left hand. For generators, we use the right hand. Right. So again, if we were to summarize the two, but before we do that, let's look at the uses of motors, our everyday uses of motors. I have only 3 examples there. There could be a lot of examples that you are familiar with. At the beginning of the motor section, I spoke of a motor gate. There are also motor roller doors. There are a lot of examples that you can think of where motors are used. Here, I only have 3 that I have used here. Motors, we find them in washing machines. Washing machines, they are rotating there, right? We also have fans. Fans are also using motors, right? And we also have microwave ovens. Microwave ovens, they also use motors. These are our everyday use of motor or in technology, right? These the way motors are used in technology. It's a lot that you can think of, great 12 learner. You can also come up with your own use that you would know of. These are just the few that I was thinking myself. Right. So before I move on, I want to just do a little recap of generators and motors, right? So we have generators, we have motors. Generators work on the principle of electromagnetic induction. Motors, the motor effect, right? Generators, we always determine the direction of current. Motors, we always determine the direction of motion. What do we use to do that? In generators, we use the right hand FBI rule. In motors, we use the left hand FBI rule, where the F is force for both, the B is direction of magnetic field, and the I is the current. Right. Design then. The design for the generators, you have 2 types of generators, an AC generator and a DC generator. A design is that for an AC generator, we're expecting to see a load, we're expecting to see a coil, we're expecting to see carbon brushes, but we are expecting, mostly importantly for an AC, to see slip rings. We must see slip rings. That's an AC generator. For a DC generator, there must be a load again. It's a generator. There must be coil. There must be carbon brushes. However, to differentiate from the AC, we must see split rings or commutator. Right. On the motor side, we must see what? We must see a power supply. We must see a battery. We must see a power supply that tells us this is a motor. We must also see carbon brushes, of course, split rings, and a coil itself. So, and when it comes to the graph representation, we should be able to draw a graph for the generators, an AC and a DC generator. For an AC, it's a generator that shows a change in direction where we go maximum to 0 to a negative maximum back to 0. When with DC, we only go maximum to 0, maximum to 0. We only have a positive maximum there. Okay, right. Let's go to our last section of today's lesson, which is transformers. These are the most simple part of electricity and magnetism, the transformers. Again, with the transformers, we should be able to define a transformer. And we define a transformer as a device used to step up or step down the voltage. That's a definition of a transformer. We define a transformer as a device used to step up or step down the voltage. We must also know, grade 12, that there are 2 types as well. There are 2 types of transformers, as there are 2 types of generators. There are 2 types of transformers. The first type is a step-up transformer. And what does a step-up transformer does? As the word itself says, step up. It is there to do what? To increase the voltage. So it's a transformer that increases the voltage. So we'll start with smaller voltage and we'll end with higher voltage, smaller, bigger, or greater. Right. Number 2, we have a step-down transformer. And what does a step-down transformer do? A step-down transformer decreases the voltage. A transformer that decreases voltage. So in a step-down transformer, we start with a higher voltage to a lower voltage. As I was talking about there in advantages, the transmission of AC current. That AC will start there with having a smaller voltage. They step it up. They use the transformer to step it up to your 11,000 volts that are moving, right, 11,000. So they're going to use a step up voltage, a step up transformer. Then it increases the voltage to 11,000. Now it comes to our houses, but it cannot enter our houses as 11,000. We must use now the second one, which is a what? Step down transformer. And the step down transformer will then do what? It will decrease the voltage as it enters our house. Right. So whether the voltage or the transformer is a step up transformer or a step down transformer will actually depend on the two things in the making of the transformer. One, it depends on the number of turns or the turns in the primary coil versus the turns in the secondary coil. So when we look at the number of turns, they will tell us whether this is a step up transformer or a step down transformer. So that again tells us by looking at a transformer, we should be able to determine whether this transformer is a step up transformer or a step down transformer. Also, by looking at the input, it also depends on the input and output voltage. Right. Okay, so let's look at a step up transformer in a little bit more detail, right? As we've said, a step up transformer, right, is the one that increases the voltage. So as we are saying here, if you are looking at the number of windings, these are the primary windings and these are the secondary windings. Look at the windings here. We have a smaller number here of windings compared to this greater number of windings here. We have a greater number of windings in the secondary compared to the primary. Just by looking at that, you are already able to determine that this is a step-up transformer just by looking at the design of a transformer. Right, so it says that the step-up transformer has more secondary windings than the primary windings. And the step-up transformer is also going to have a greater output voltage than the input voltage. And if asked, because we could be asked to do some calculations there of either the input voltage, the output voltage, the primary windings and the secondary windings, this is the formula that we have to use, where Vs stands for secondary voltage, voltage in the secondary windings, Vp stands for primary voltage, Ns stands for secondary windings, Np stands for primary windings. Right. So that's a step-up transformer in details, and that is actually all that we need to know when it comes to a step-up transformer. Right. What about a step-down transformer? A step-down transformer is a transformer that decreases the voltage. If you look at the number of windings, it will have more windings on the primary as compared to the secondary coil. So as you can see there, we have greater here compared to smaller on the secondary. We have greater compared to smaller on the secondary. So as it says there, the step-down transformer has more primary windings than the secondary windings. And the step-down transformer has greater input voltage. So the input voltage will be bigger than the output voltage. Again, we could be asked to calculate one of those variables there. We could be asked to calculate the secondary voltage, which is the output voltage, or the primary voltage. We could be asked to calculate the secondary windings or the primary number of windings. And this is the formula that we use for such. We'll be taking an example in a moment, and I will be showing how simple it is to get these marks, such that no learner should ever get a question wrong when it comes to transformers. This question, you must get all the marks, because there is not a lot that we need to do. We don't even need to know the principle under which the transformers work. We just need to know the definition. We need to know that we have two types of transformers. We only need to know that we have a step up and a step down transformer, and we need to know how to identify one in terms of a diagram being given. We see the number of windings. If we have more windings on the secondary than the primary, it's a step up. If we have more windings on the primary than the secondary, it's a step down. We also look at the voltage. If more voltage output, step up. More voltage input, it's simply a step down, as we go to the example I was talking about. So here's our example here, right? Example 1 says, a step-up transformer is used to convert a potential difference of 120 volts to 100 kilovolts. If there are 50 turns in the primary coil, calculate the number of turns on the secondary coil. So as I've said, we could be asked to calculate one of those variables. And how do we do that? We simply do that by going to what? Going to the formula. It is very simple. You go to your data sheet, you go to the formula sheet, we go to electromagnetism there. You will find this formula as I have shown you at the beginning of our lesson, that this is the formula we're going to be focusing on for today's lesson. And what does the formula say? The formula say Vs over Vp is equals to Ns over Np. So what you want to do here, you want to collect your data. That's the best way you can identify which one is missing. So before you can use the formula, it is very, very important with transformers to actually do what? Actually collect the data. So let's actually collect the data and say what is given. I can see there they are saying it's used to convert a potential difference of 120. So that's the input voltage. So I have Vp 120 volts, 200 kilovolts. So that means I also have the Vs 100 times 10 to the power 3, because kilo means times 10 to the power 3 or times 1,000 then, right? If there are 50 turns in the primary core, that means I am given Np, which is 50 turns, right? Okay, calculate the number of turns in the secondary. Ns is what I am looking for. So simply from that fact, I just go to my formula, and then after I've collected my data, I substitute and I do the mathematical manipulations and I get to the answer. What is my Vs from the data? My Vs is 100 times 10 to the power 3 or 100 times 1,000, right? However you want to write that, kilo over Vp. Vp is given as 120. This is equals to Ns is what I am looking for. So I'll write it as Ns for now, over Np. What is my Np? My Np is 50. From here, what do? I simply cross multiply. That's the mathematical manipulation that I need for this topic, or for this for the transformers. I will always be cross multiplying. You will cross multiply, then from there you will divide and get your answer. Always it will only be that mathematical manipulation. So if I cross multiply, I will get 120 times Ns is equals to 100 times 10 to the power 3. I do not want to press my calculator yet. I always like to press my calculator once if possible. Multiply by 50. Now I'm looking for Ns. So since 120 and Ns are multiplying, the only way I can get rid of this 120 this side is by dividing by the 120. What I do on the left hand side must also be done on the right hand side of an equation. That's the golden rule of equations in maths. Then from there, I take my calculator, I calculate, right? I need 100 times 10 to the power of 3, multiply that by 50, close the bracket, all over 120, not 120, all over 120, not the 20 that I have written down there. Almost made a huge error there. I should get that the number of turns is 41,666.7. However, I will round it off to 41,667 turns, as these are actual turns. We're not going to have a point something 10. So it's going to be 41,667 turns. That's the number of turns that I am going to be having there. Right. Let's look at the second question in our examples. It says a transformer has 1,400 turns on the primary coil, 120 turns on the secondary coil, and a secondary voltage of 20 volts. Determine the value of the primary voltage and whether this is a step up or step down transformer. So for this one, after we've determined the answer, we should also determine, was this a step up or a step down transformer? We could have done this as well with this one, right? This one was obviously a step up transformer, as we see the output voltage is greater than the input voltage. We also saw the number of turns were greater in the secondary coil. We got 41,667, which is way greater than 50 turns. So that's the knowledge that we are going to use in determining whether this one is a step up or step down transformer. Right. What formula are we using? We are using Vs over Vp, which is equals to Ns over Np to calculate. Very, very simple mathematical calculation. Before we can do anything in transformers, we want to collect the data. So it always makes it simple and clear if we collect the data. So it says there a transformer of 1,400 turns on the primary coil. So I already have Np is 1,400 turns. Right. 120 turns on the secondary. So I have Ns 120 turns. Right. And a secondary voltage of 20 volts. So I have Vs. It is 24, not 20, 24 volts. Then it says determine the value of the primary voltage and whether this is a step up or step down transformer. So it means the only variable I don't have here is Vp. So I go to my formula, I substitute and I determine the Vp. So Vs, I do have that is 24. Vp, I don't have that. Vp equals to Ns. Ns is 120. Np is 1,400. But by looking at the number of turns, already I hope at least one of you or all of you now are able to tell whether this is a step up or step down transform. So even if I make some mistakes in my calculation, I should be at least able to get this mark of identifying whether this is a step up or step down, because in actual fact, I don't necessarily need to do these calculations to determine whether this is a step up or step down. Without doing the calculations, I could determine that as well, right? But we'll see as we continue how we could have determined whether this is a step up or a step down transformer. So from here, what do? The cross multiplication that we're talking about. So we have Vp times 24. So it's going to be 24 Vp, which is equals to, right? Not 24, but 120 Vp, which is equals to 24 multiplied by 1,400. And to get the Vp, I should divide by 120, divide by 120. This cancels this. The Vp, the primary voltage, was how much? So I should multiply 24 with 1,400. Divide that with 120. I get that the primary voltage was 280 volts. It was 280 volts. And that 280 volts was the primary voltage, which was greater than the secondary voltage, telling me that here I am dealing with what? I'm dealing with a step down transformer. Right? But I could have been able to tell this answer without doing these calculations by looking at the number of turns. If I look at the number of turns in the primary, there are 1,400 turns, and in the secondary, I have 120. So I have more windings on the primary coil than I do on the secondary coil. That just clearly indicates to me that this is a what? This is a step down transformer there. Right, so that is it with when it comes to transformers as well. We've looked at what transformers are. Then let's quickly do a small recap of transformers. We say transformers, we must define them as a device used to step up, step down the voltage. And we must know that there are two types of transformers: a step up transformer, which is a transformer that increases the voltage, and a step down transformer, which is a transformer that decreases the voltage. Right? So we must be able to look at the design of a transformer and be able to tell whether it's a step up or step down. How do we tell a step up? It's going to have more windings on the secondary coil than on the primary coil. And it's also going to have a greater output voltage than the input voltage. Right. And then what about the step-down transformer? The step-down transformer is going to have less windings on the secondary coil than the primary coil. And then it's going to have a smaller output voltage than the input voltage. Right, grade 12. Let's look at this simple activity that will take us a few minutes and then see if we can be able to answer it correctly. Question 14 then says electromagnetic induction. Start on the new page. A coil is turned into a uniform magnetic field, but X and Y moves downwards with respect to the horizontal. The diagram shows the position of the coil the moment that it lies parallel to the magnetic field. This is very important. The moment that it lies parallel to the magnetic field in the horizontal plane. Right. Then they ask 14.1. What type of generator is illustrated? Explain your answer. What type of generator we're going to say is illustrated? There we must explain. Well, definitely it is a generator. Right? There is no battery, there is no power source, so it's not a motor, it's a generator. Right. So what type of generator is illustrated here? And the answer there is, this is an AC generator. And then they say we must explain our answer. And the explanation there is going to be, it has slip rings. Right. Then they ask, in which direction does the current flow in the coil? Right. And to get the direction, we must use our right-hand FBI rule. Right. And the direction of motion there, they are telling us it goes down. So as we go there, there's a direction of motion, but the direction of the magnetic field goes from north to south. And as we can see there, so it means we must hold it like this, north to south. Then direction of motion goes down in the XY. So that tells us the direction is what? X to Y. It is X to Y. Sketch the voltage time graph for the generator for one circulation in rotation. And to do that, as we can see, since they say its moment it lies parallel, it means it is starting there where it produces the maximum. So one rotation there should go to 0, and it goes to a minimum maximum, goes back here, and this will only give us the rotation. So this would be the PD in volts, and this would be the time in seconds. Right. As you can see there, the solutions are looking like the way we determined them. Right. So this is it, grade 12 for today's lessons. Thank you for being with us, and I hope we enjoyed the lesson, and I hope we understood everything. Thank you.